First of the conic sections is presented in 6.2, and that is the circle. We actually have a lot of experience with circles already, so hopefully some of this is review. A circle can be found by taking a cone, a double cone, and slicing it horizontally. Slice. And there's our beautiful circle. If there was any sort of tilt to that slice, then we'd end up with something else, something called an ellipse. But right now we're just going to focus on this one special shape, the circle. We actually started talking about circles a long time ago, at the beginning of the year, when we talked about vectors. We might have had a problem like this. Imagine there is some point C. C is on a graph. And let's just say it's at 2, 4. So 2 over 4 up, we've got this point called C. Now, C could be part of a vector. Let's call the vector CP. So that's how we represent a vector, where C is the start of this vector and P is the end point of this vector. And let's say that the magnitude of this vector is equal to 5. And that P is just some point with coordinates xy. Some point xy. The question is, where can you put the point P? Can you put it anywhere? Can it go just one spot? Can it go an infinite number of different spots? Turns out we can put this point P in lots of different places. So just as long as it's 5 units away from C, then it works for this vector equation. So to solve this vector equation, we could put P over here, to right around here. And just as long as it's 5 units away, we could say the coordinates of this are 7, 4. If I move 5 to the right of 2, 4, I'm at 7, 4. I could have gone straight up. And to go to 2, what is that, 9? I could have gone to the left. That would have taken me to negative 3, 4. All these points P satisfy the vector equation. And they are not the only points that satisfy the equation. These are just the easiest to find. These are the points north, south, east, and west of the center point. Because we could also have a point like maybe over here somewhere. Here's another possibility for C. C could have been lots of different places. If we were to collect all the possible positions of point P, then we end up with a pretty circle. This is actually called the locus of points, and that's one of the definitions of a circle. A circle is the locus. Locus is L-O-C-U-S. The locus of points equidistant, big word there, from a fixed point. That fixed point is the center of the circle. In this problem, the fixed point is C. Locus just means a set of all points. Set of all points. So these red circles actually aren't part of the locus, but if I were to improve the picture a little bit, all of these points, as long as they're 5 away, 5 away, 5 away, then they are part of the circle. Alright, good. Another way to think about this is, let's say you got a dog on a leash attached to some sort of pole, and you let the dog run around. Well, guess what path the dog is going to follow? There's the adorable old dog. He just runs around in a circle. Okay, so every position the dog can get to is part of the locus of points that makes up that circle. So let's get rid of a bunch of these points here. I don't want these points here. Let's just pick one random spot on this circle. Close it up. And let's not associate any numbers with this random P. So I'm going to pick a P right here. Let's do it in blue. There's point P. Okay, so in order for this point P to be on the circle, I just have to make sure that the length of the vector, or if you prefer, the length of the segment between C and P, is 5. Well, we just got done with 6.1 where we used the distance formula quite a bit. The distance formula is a way of defining the length between 2 points. The distance formula is just x2 minus x1 squared plus y2 minus y1 squared. This comes directly from the Pythagorean theorem. If we apply this formula to this situation, this vector equation situation, we're going to end up with a nice formula for this circle. Just like lines have equations, like y equals 3x plus 7, and parabolas have equations, like y equals 3x plus 2, circles also have equations. And we can find that equation by using the distance formula. In this situation, I already know the distance. The distance between the 2 points I've defined as 5. So 5 equals the distance, the square root of x2 minus x1. So let's see here. It doesn't really matter what which one I consider x2 and which one I consider x1. But traditionally, we say that the outside is the first x2 rather, and the inside is what we subtract. So we end up with x minus 2, that's this minus this, plus y minus 4 squared, that's this minus this. And this essentially represents an equation in terms of x and y for any point on this circle. Even if point P was way over here, point P would still have coordinates, and the coordinates would still satisfy this equation. It's usually not written this way though. It's not written with a big square root in there. So in order to just clean this up, we can square both sides, and we get this equation here. X minus 2 squared plus y minus 4 squared. And I forgot that I'm squaring both sides. The whole point of that is to get rid of the square root. So this is actually a more traditional representation of a circle. This is called a Cartesian equation because it uses coordinates, the Cartesian coordinate system. The center of this circle you can find right there in the formula, 2, 4. And the other part, the other information in this equation is the radius. The radius, though, isn't 25, it's the square root of 25. If we were to generalize this equation completely, it would look something like this. Instead of c being at 2, 4, if we generalize this and just say hk, for instance, and if we don't say that the distance is 5, instead let's say that the distance is just r, then it's going to change our formula just a little bit. This isn't going to be 5 right here. This is going to be r. Instead of x minus 2, it's going to be x minus h. Instead of y minus 4, it's going to be y minus k. And when we take this next step of squaring everything, we're not going to get 25. We're going to get r squared, and everything else follows suit. So this equation here is the general formula for all circles, where the center of the circle is hk, and the radius of the circle is r, keeping in mind that r is not directly in the formula, it's actually r squared that's in the formula. And then xy, of course, well, what xy represents is any point on the circle, any point that is part of that locus of points. Any point on the circle is called xy. So let's take a look at the next example here. And we can use this formula for a circle, which I'll redo in green here. That was really bothering me that it was written all diagonal like that. So this is the general form of any circle here. And let's apply this to the next example, example 2. No, this is not example 2. This is example 1 out of the book, part A. And part A is pretty straightforward. It says find the center and radius of each circle. So we have the equation x minus 3 squared plus y plus 7 squared equals 19. If we use the formula that we developed above, we can find h and k pretty directly. In this problem, h and k are equal to 3 and 7. That represents the center of the circle. And the 19 in that equation, 19 isn't r. The 19 is r squared. So r is the square root of 19. And hopefully by now you've caught my mistake. The mistake is the center here. This isn't 7. It's actually negative 7. The reason being, this is x minus 3, but this is actually y plus 7. You can think of y plus 7. Y plus 7 is the same thing as y minus negative 7. And this formula for a circle is set up with negatives right in there. It's y minus k. So if you have an addition sign, you just always find the opposite. The center can be found, the coordinates can be found using the opposite numbers. So let's take a look at what this circle is going to look like. I have in this top row here the general equation for a circle. X minus h squared plus y minus k squared equals z. But z is equal to r squared, and I can change r with this slider here. I can also change h and k with this slider here. But the way I have it set up right now matches up with the problem right here, or the circle right here. X minus 3, y plus 7, and then equals 19. So that z is 19, and that's what I have right here. But I can modify z by modifying r. It's not exactly 19, but it's close enough. So let's take a look at what happens when h, for instance, gets bigger. So it's at 3 right now. I'm going to move this to the right, and it's going to also move to the right, and I can move this to the right, and it's going to move up right there. The h controls the left and right, so here we have a circle whose center is at x coordinate negative 4.65. The k is going to move it up and down. This is like the translation we were doing before with all the other graphs we've been working with. We were moving sine waves up and down and left and right. We were moving parabolas left and right and up and down, square root graphs up and down, left and right. Same kind of idea here. It shouldn't be any surprise that if we take this radius and increase the number, it's going to increase z. So we have r equals 8, this z is equal to 64. We have a much larger circle. R, let's see what happens when r gets really small, really small. Now it's 0, there's no circle there, and that makes sense. A circle with no radius at all doesn't really exist. And then here's something a little more abstract. If r is a negative number, you still end up with the same type of circle here, because when you square this negative number, you're still going to get a positive number, so it doesn't have a huge impact. Okay, so that's introduction to circular formulas, and I hope you've enjoyed watching as much as I've enjoyed putting it together. Goodbye.